I wanted to put up the course roadmap first because we really are rolling through these topics. We're making really good progress. You are making really good progress through these multiple topics and essentially multiple classes that these topics span traditionally in electrical engineering. So we've worked through all the circuits topics from DC all the way up through sinusoidal analysis. We covered semiconductors, we covered diodes and transistors, and we've stepped into the topic of operational amplifiers. And so last time we talked about what an operational amplifier is, what it does. We talked about negative feedback, and today I'm going to expand on that a little bit and show you another type of op-amp circuit that's very useful, very practical. And also today, once we finish up op-amps, we're going to step into the digital logic and digital systems topic. So it's going to be a good lecture today, I think. It's one of my favorite set of topics. So before we get started with the topics, the simulation lab number 4 is posted, so take a look at that. Also, don't miss the pre-lab. There is a pre-lab associated with that lab. The videos will be linked up there shortly. So after class, give me a couple hours after class and I'll link those videos up there. Also, take a look at the assignments page for the homework assignments. 6 and 7 are due this week, and quiz 5. So there's this gap between quiz 4 and quiz 5, so don't miss out on quiz 5 this week. And as normal, my office hours will be right after class, so I'll keep the Zoom session up if you want to ask questions or hear other people's questions. And as always, if you have a question, please unmute or shoot me a chat, and otherwise stay muted to keep the background noise down. And if I drop off during the lecture for technical issues, stick around for a few minutes. I'll try my best to get back. Knock on wood, hasn't happened yet. But if I keep preparing for it, maybe it won't happen. Okay, so that's the course roadmap. What I'd like to do is show you, kind of dig into the op-amp a little bit more. So I'm going to bring up some op-amp slides here. Okay, so here you should be seeing now a slide that says operational amplifiers. And what I wanted to show you is really what the electronic circuit, what the integrated circuit looks like for an operational amplifier. This is an op-amp. This is a chip. This integrated circuit has op-amps inside, and it actually has multiple op-amps. So what this is this is a package that fits on a circuit board or a breadboard. It has 14 pins coming out of it, and this diagram on the right is actually inside that op-amp, kind of a cartoon view of what's inside the circuit. There are actually 4 op-amps in this integrated circuit, and so at the lower left you can see pins 1, 2, and 3 are actually the output and the inputs to op-amp number 1, and then you can see 3 other op-amps here. The power, the VEE and VCC that we drew on the schematic symbol for last class, that's actually labeled here as V plus and ground, right? So it's a little confusing if you work with these in the future. In reality, V plus is VCC, ground is VEE, and don't confuse V plus with the non-inverting input to the op-amp. And also ground, in this case, for this chip, does not have to be 0 volt ground. You can actually have a negative supply applied here so that you can actually get negative voltages out of the op-amp output. We'll talk a little bit about that. But this is what an op-amp physically looks like, one package of an op-amp. There are other packages, but that's what it looks like. This is actually a simplified schematic of one of the op-amps inside the chip. This is an LM324, one of the op-amps. And so this explains how it works from the data sheet. And you can see all the transistors inside this op amp. This is a current source up here. You can see the V+, this is VCC. The grounds are actually VEE. And you can kind of see this. You can see that for all of the NPN transistors, or the ones here, the collectors are connected to what would be called VCC, and the emitters of the NPN transistors are connected to what would be called VEE in our diagram. So the inputs on the left here are the inverting and non-inverting inputs. And so then there's some stages of amplification. There's some current sources supplying current to these transistors. And then here's the output right at the output. So the point of an op amp is, instead of having to worry about designing an amplifier, a high gain differential amplifier, TI or Analog Devices or National Semiconductor, they've done it for you, and they've packaged it in an integrated circuit, and then you can use this op amp like we talk about in class, either an amplifier circuit that we've talked about or a comparator circuit that we will talk about. Okay, so I just wanted to give you that view, and again, if you have any questions, just shout them out or text me. So let's step back and talk about op amp circuits. I want to show you another set of slides. So you should be seeing a slide now that says comparators. Let's talk about comparators. Comparators are op amp circuits. And so first I want to show you how to look at a circuit and say, hey, that's a comparator, or hey, that's a linear amplifier. They're two different things. First, let me say you kind of already know what an op amp linear amplifier looks like. It's what we did last time. The non-inverting amplifier and the inverting amplifier are two examples of linear amplifier circuits made with an op amp. They multiply the input signal by a number, and you get an output. That's one type of linear circuit. A comparator compares two voltages, right? It's right in the name. It compares two voltages, and it tells you if a voltage is higher than the other or lower than the other. So that's what a comparator does. It compares two voltages, and that's useful for, let's say, a thermostat or a pressure sensor or a light sensor, where you have a threshold against which you want to compare some sensor value. Now, in looking at analyzing an op amp circuit, here's some guidance. So this is actually how when you look at a circuit, you would decide how to analyze it. So here's the decision tree. I'm going to create a decision tree here. Let's suppose you have an op amp circuit, and you look at the circuit, at least in this class, all the circuits you'll see. It has an op amp. You're going to make a decision here whether the circuit has negative feedback or not. Remember, you can identify negative feedback in a circuit by finding any connection from the output to the inverting input of the op amp that doesn't go through ground or doesn't go through the power supply. But it could be a resistor, could be a set of resistors. But if you see some output, some connection between the output and the inverting input, you can assume you have negative feedback. And so now, once you have negative feedback, you know you have a linear op amp circuit. It could be an amplifier. It could actually be an integrator or a differentiator or a summer, but it's a linear op amp circuit. And once I have identified that it's a linear op amp circuit, then there's another decision to make. If you don't recognize the circuit, you don't see it as a common circuit that you've seen before, then you do what we did last time. You use the negative feedback approach. You assume that the input differential voltage is 0. You assume that the input currents into the op amp inputs are 0, and you use KVL, KCL, Ohm's law, whatever, and that's how you analyze it to find whatever you're trying to find, a voltage or a gain or whatever. If you, going back to the last class, if you recognize the circuit, you say, hey, that's an inverting amplifier, right? Because all of the resistors are connected just like they were in the example that we showed. Or that's a non-inverting amplifier. All the connections are the same. Then we derived an expression for gain. So I would name that a common circuit, right? It's a common circuit. Basically, if you've seen it before and you know the gain equation, then call it a common circuit and you don't have to use the negative feedback approach. Okay, so if you have negative feedback, it's a linear circuit, and you use one of these two approaches to, well, figure out whatever you're trying to figure out about the circuit. Okay, let's now dive into what we did not cover, have not covered yet. That's the case where you have no negative feedback. In other words, there's no identifiable connection that doesn't go through ground or a power supply. There's no connection that between the output and the inverting input. The inverting input. Okay, in this case, in this class, that will always be a comparator, and usually it is a comparator. A comparator compares two voltages, right? So then there's a decision to make. Now there are different kinds of comparators. We're going to group them into two different kinds. So you're going to make a decision here how to analyze it. The comparator is either a simple comparator, and by that I mean a comparator that compares two voltages, and if one voltage is higher than the other, you get a high voltage at the output. If the opposite is true, you get a low voltage. It's just like I'll show you, like a thermostat circuit. Or if it's not a simple comparator, and I'll show you examples of these, then in this class, it's a comparator with hysteresis. So I'll show you what hysteresis is. It basically means that you have multiple thresholds. So instead of one simple comparison, you're comparing against a threshold that's based on a past value. There's hysteresis there, and we'll talk about that. So this is an important diagram when you're working an op-amp circuit. So this is one to maybe print out and put aside. If you have an op-amp circuit, this is how you make your decision on how to analyze that circuit or what it is. Okay. So what I want to do is I want to talk about the limitations of an op-amp, because some of the limitations are not so good. You can use an op-amp outside of its normal bounds and it won't work like you want it. And actually one of the limitations is good. One of the limitations, output voltage swing, is what makes a comparator work. Okay, so we're going to use a limitation as a feature. So let's take a look at that. Let's talk about op-amp limitations. One of the limitations is output voltage swing. Okay, so this has to do with the output voltage of an op-amp, and the swing means the span of it. How high can it go? How low can it go? So the op-amp output voltage must be between, it will fall between the power supply voltages. So, a way of drawing that is if you draw an op-amp with its VCC and VEE, right, the positive supply and the negative supply, then the output has to be between VEE and VCC, right? That's where the output is coming from. It's going to be somewhere between the two power supply voltages. So there's usually some margin between the output voltage and VEE and VCC. What's that mean? That means that Vout can never really go all the way up to VCC. Vout can never really go all the way down to VEE. Okay, it's going to fall somewhere in between, and it's never exactly equal. Some of the really cheap op-amps, they might have a volt or two margin. So Vout might go to, let's say VCC is plus 15 volts. Vout might only go to 13 volts. Some of the more expensive op-amps, again, expensive is relative, but some of the newer higher end op-amps are called rail-to-rail op-amps, and they get really close to the power supply voltages, or they can for the output. So they're, again, we're going to use this limitation as a feature for comparators. Okay, to give you an example of an excerpt out of a data sheet. So this This is a table out of a data sheet for these 3 op amps. They're all in one data sheet. This is the output voltage swing, and it shows VOH is the high output value, VOL is the low output value. They specify in this data sheet the output values based on the load resistor. So now, how much the voltage that you can get out of an op amp depends on how much current you are taking from the op amp, which means by Ohm's law, what resistance you are attaching to the output of the op amp. And so, this manufacturer lists a V plus of 30 volts and presumably a V minus, right, or a ground of 0 volts. And what it's showing here is that, for example, for this LM324, even though you've attached a 30 volt power supply, if you have a 2K ohm resistor attached to the output, it can only output up to 26 volts. So there's a big margin there, 4 volts between the output voltage and the power supply voltage. So don't expect to go higher than 26 volts. You can get to 25, you can get to 26. This is a minimum, so maybe 26.5. I wouldn't count on going higher than that. And so at the low end, VOL, you can actually get all the way down toward near ground. So presumably, and the manufacturer doesn't list it, but you could get really close to VEE, even if it were a negative voltage. Okay, so we'd have to dig deeper into the data sheet to figure that out. Okay, so that's an example of output voltage swing, something we're going to use as a feature. It just says that the output must fall between the power supplies. The voltage of the output must fall between the power supplies. Okay, so that's one limitation. Another limitation is the output current limit. So you would guess that the output of a real op amp, a practical op amp, is limited to some maximum value. So the currents out of and into, because an op amp's output can have current coming out of it and it can have current going into it. Those values are limited to some maximum value. And so if I were to draw an op amp, this is what I'm calling I out. And so the output current limit means that for some positive I out has to be less than some maximum value. Okay, and so when the op amp is outputting current, we would say that the op amp is sourcing current. It is a source for current, right? When I out is negative, that means current is actually positive charge is flowing into the op amp's output. That's fine, it can do that. We call that a sink. So when you hear sink, that means current is going into the device. So it's sinking current. And so negative I out means that that you're limited to the amount of current that can go into the op amp. So you just have to design for it. What some folks usually miss in practical examples, and this helps explain something about the op amp circuits we looked at last time, you also have to consider the feedback path in the I out, because the op amp is actually supplying current to whatever load it's connected to. It could be some speaker, it could be some data acquisition device. But also remember, last time we connected feedback resistors, and there was current flowing through those feedback resistors. So if there's a milliamp flowing down through that feedback path, and you only have 10 milliamps to work with, I out max, then you can only have 9 milliamps going out to your load. So your feedback path actually takes some of that current. That's important when you consider, and I didn't bring this up last time because we hadn't talked about this, but the inverting and non-inverting amplifiers, their gains are dependent on the ratio of resistors, not the absolute values of the resistors. Well, here, this is a consideration here. You don't want your resistors too small, because if your resistors are too small in your feedback path, then you're going to use all of your output capacity of your op amp in your feedback path. So when you're, in the future, you're designing something for some future class, don't make these resistors in the feedback path too small, because by Ohm's law, that would require a lot of current, and you're going to use up all of your current capacity of your op amp. Now, on the other end, you don't want those resistors too large for a couple of reasons. One, your amplifier gets noisy. We're not going to derive that, but I'll mention that. And also that the negative feedback assumptions that VID goes to 0, that assumption actually starts falling apart if you use very large resistors. So typically you use resistors in the few k ohm, greater than 1 k ohm, up to maybe 100 k ohms, maybe 50 k ohms. But if you start getting into the meg ohm and 10 meg ohm and larger, your op amp circuit won't work like you would expect. Okay. So an example out of a data sheet is this. So this is the LM324 op amp and its cousins here. So the output current that it can source at a 2 volt level. It was tested at 2 volts output. It can source minimum 10 milliamps, typical 20 milliamps. Okay, there are variations chip to chip, but you're guaranteed at least 10 milliamps capacity output of current. And it can sink, if you look at the LM324, between 5 and 8 milliamps. So it's different. It can output more current than it can actually take into its output. So it's something to pay attention to. So if you're designing your resistors up here in your feedback path and you use 4 milliamps in your feedback path, then you've used actually most of your capacity for sinking current. So something to look at. So consider the current required by the load connected to the op amp, and also consider the current through the feedback path when you're designing a circuit. Okay. So some practical advice there that sometimes is left out of circuits class. So what is a sink? A question came up. What is a sink again? So to source current means to output current. Okay, to have current, positive charge flow coming out. If I am sourcing current, I am outputting current. To sink current, I am taking current in. In other words, I'm outputting a negative current, which means I'm taking in a positive current flow. What that means on this diagram is if this op amp is sourcing current, then current is going from left to right. It's coming out of the op amp. If the op amp is sinking current, then current is coming from the output, from the outside of the circuit into the output. Okay, and you might ask, where is that current either coming from or going to? It's either coming from, like if you're sourcing current, it's coming from the positive supply. So there's not a positive supply shown here, but if I showed it, the current would be coming from the supply voltage source into the op amp through all those transistors that I showed, and then out of the output. If let's suppose there's a load resistor connected and you've created a negative voltage at the output node here, then current would be coming up through that load resistor from ground, because this is a negative voltage, and into the op amp. And where does that current go? It goes through all those transistors and out the VEE node to the negative supply. Okay, so that's where the current comes from. So it's kind of deceiving here. If you look at the whole op amp, I said, well, wait a minute. Op amps have high impedance inputs, so there's very little current, negligible current, going into or out of these inputs, but yet the output has, well, 10 or 20 milliamps, up to 10 or 20 milliamps coming out. Where's that coming from? It seems to violate KCL. It's coming from the sources, which aren't shown here. Okay. All right, so that's the output current limit. So we've talked about voltage limit, we've talked about current limit. Let's talk about slew rate. So sometimes we forget about slew rate. Slew rate does this. It limits the rate of change of voltage, of the output voltage. So in other words, the slope of the output voltage, how fast can it change over time, its slope. It's limited to a maximum value. So it's how steep the slope can be. In other words, how can I go from 1 volt to 5 volts in 1 microsecond, in 1 nanosecond, in 1 picosecond, right? How fast can I change the output? The slew rate is the name of the limitation that tells me how fast I can change the output voltage. And you may care about that if you have a sine wave, right? Or if you're amplifying audio, how fast you can change the output. The maximum value that the output voltage can change over time is called the slew rate, and it's specified in volts per second or volts per microsecond, right? So volts per time. And so if you have some V out of t, just some value, the derivative of V out of t, its slope, the absolute value of that, has to be less than the slew rate. Right? The maximum slope, either positive or negative, is the slew rate. And so this is a kind of a diagram of it. Now, let's say you're at time equals 0 right here, and your waveform is changing. Your waveform would have to vary within these bounds. It could go up with the slope that my mouse is tracing here, but it could not go up with the slope that my mouse is tracing there. Now, at every point in time, you have to consider this slew rate, right? I've just drawn it at t equals 0, but at any point in time along the waveform, you cannot exceed the slew rate defined by the manufacturer. You can find that in the data sheet. And so from a data sheet, here's a slew rate for the LM324, and the slew rate here is 0.5 volts per microsecond. Okay, so that's 500,000 volts per second. That's I'm going to call it a speed. It's a rate of how fast you can change the voltage. Now you can also relate slew rate to frequency. You can imagine if you have a sine wave versus time here, the sine wave has a slope. Its steepest slope is when it crosses 0. And the higher the frequency, the steeper the slope. So the slew rate can be related to how high of a frequency can you amplify with an op amp. Right? So you just take the derivative of sine, get a cosine, and figure that out. But so slew rate relates to how steep can you have a slope change, and how high of a frequency can you have at the output of an op amp. Okay, so those are the limitations, the common limitations of an op amp that really appear in most designs. You have to know, well, I want an output of negative 10 volts. You got to pick the right op amp voltage swing. I need 22 milliamps. Well, you need to pick the right op amp. Then you look at the data sheet, or I need you know, I've worked with op amps that are up to 6,000 volts per microsecond. I needed a very fast op amp. So 6,000 volts per microsecond, you can buy those from Analog Devices and other manufacturers, but this is 0.5. This is a cheap op amp. This is 0.5 volts per microsecond. I was using 6,000. That's what 12,000 times faster. It costs more, and so you have to. That's why there are so many different op amps out there, because there's every application is different. You may need a low cost op amp. You may not care about cost. You just need a fast op amp. So lots of different op amps out there. This LM324 is a really common op amp if you're just building kind of an audio frequency project or a DC sensor project, slowly varying voltage project. This is what you'd use. Something like this. Get them for probably less than $1. So, okay. And if you have any questions on this, again, stop me anytime. I'll keep going through the op amp material. So what I'd like to do now is apply this to comparators. Oops, I did that too early. So let's talk about comparators that compare two voltages. So roughly described, and I'll show you this on the whiteboard, the output of a comparator is either high or low. So if you have a 5-volt power supply and 0 volts connected to VEE, I'll show you that, then when I say high, I mean 5 volts. When I say low, I mean 0 volts. So if one voltage is greater than the other, you're going to see 5 volts at the output. If the opposite is true, you're going to see 0 volts at the output. Again, the circuit is comparing two voltages, and it's giving you an indication at the output by either outputting a high or a low. So you can make decisions using this kind of circuit. You can use an electronic circuit to compare, is the temperature too hot or too cold? Is the pressure too high or too low? Is the light too bright or too dim? And do something about it. Your circuit can respond to that. So that's what a comparator lets you do. Okay, so what I'd like to do now is move over to the whiteboard and talk about a comparator. So you're going to see my computer screen go away, and you see my whiteboard come up. Okay, so at this point, you should see my whiteboard fairly full screen. So what I have drawn here, and again, if there's ever any problem with the focus or anything, please let me know. In fact, let me hit autofocus here so I can make sure it's in focus. But if it's not in focus, let me know and I will straighten it out. And I also have to bring up the chat. Okay. So this is an op-amp circuit. It just has an op-amp. Well, that's it. It has an op-amp connected to a power supply. So I have the op-amp connected VEE to ground and VCC to 5 volts. So what's that mean? That means there's one 5-volt DC power supply with its negative side connected to VEE and its positive side connected to VCC, creating that node voltage. And I have the two inputs labeled like we labeled them last time, V1 and V2, for the non-inverting and the inverting inputs respectively. And then the output is shown here. And I have the output of the op-amp drawn in as we defined an op-amp to be a high gain differential amplifier, right? High gain. AOL is some big value. The differential voltage VID is V1 minus V2. So I want to do something here. Let's define a big AOL. It doesn't really matter what it is, but let's say it's 10 to the 6th. That would be a pretty big AOL. AOL varies if you look at data sheets between 10 to the 4th and 10 to the 6th, somewhere in there. But again, it doesn't really matter what it is. It just has to be big. So let's do this. Let's assume I have no negative feedback. All I have is this op-amp connected like it is, and I have I can apply a V1 and a V2 at the input. Let's create a table here: V1, V2, and V out. So I want to make a table, and we can apply a V1, we can apply a V2, we can measure with a voltmeter V out. That's all we're doing. There's no negative feedback, no connection between the output and the inverting input. Let's just pick two values. This is going to help explain how a comparator works. Let's just pick two values. So V1, let's say, is 4 volts. V2 is 3 volts. So I connect two power supplies, I create that. Okay, so V out is, well, 10 to the 6th AOL times V1 minus V2. V1 minus V2 equals 10 to the 6th, right? I'm going to get 1,000,000 volts out of this op-amp according to the textbook equation. Well, that's not going to happen, right? We know from the output voltage swing limitation that the output has to fall between VCC and VEE. So you're not going to get 1,000,000 volts. You only have 5 volts. So at the top end, at the positive end of the range, you're not going to get 10 to the 6th. You're going to get approximately VCC. Okay, because we saw there was some margin. I'm just going to say, just for the sake of simplicity, that we're going to call it approximately 5 volts. Okay, it might be 4.8 or 4.7, but you'll get approximately 5 volts out of the op amp. So if V1 is greater than V2, right, just like it is here, then you're going to get a high value out of the op amp. Let's suppose the opposite is true. Let's have an input of, I don't know, 2 volts at V1 and keep 3 volts at V2. So a little space there, 2 volts, 3 volts. And again, textbook formula, 10 to the 6th times 2 minus 3 equals negative 10 to the 6th volts, right? So you're going to get negative 1,000,000 volts out of this op amp. Well, you're not really, because output voltage swing says that you can't go lower in the negative direction than VEE. So this isn't going to happen. You're going to have approximately 0 volts, which is approximately VEE, okay? So if V1 is less than V2, you get a negative value for VID, V1 minus V2, and you get a negative big value, which is going to be limited by VEE. So this is a way to create a circuit just with an op amp that compares two voltages. Now you say, wait a minute, what if let's see, what if V1 is 4 volts and V2 is 4 volts plus 1 microvolt, right? Because 4.00001. Well, yeah, at that case, if you could hold those voltages noise free, then I guess in theory you could get 10 to the negative 6 times 10 to the 6th equals 1 volt. In reality, you can't, not very easily, it would be very difficult to create a voltage that is noise free such that it looks like DC down to the microvolt level, right? So it'd be very difficult to actually demonstrate that. You couldn't do it in lab very easily. So usually your differences in voltages at least are on the order of millivolts, and if the differences are on the order of millivolts, then this holds true, that you're actually comparing two voltages, even if they're different by only a few millivolts. This comparator would work. Okay, so let's define what kind of what we want to do with a comparator. Let's suppose you want to build a thermostat. So maybe you have a I don't know, something like a temp sensor, right? So I'm just going to draw a block diagram. That's a temp sensor, and maybe that outputs a voltage to, well, a comparator, and maybe that outputs a voltage to a heater, right? It's not powering the heater, it's just a control voltage for the heater, such that when the output voltage is high, the heater turns on, and when the output voltage is low, the heater turns off. So let's look at this circuit, this block diagram, from the perspective of the comparator. We're going to say there's some input voltage to the comparator and then some output voltage from the comparator. Okay, so the comparator is taking an input voltage, it's outputting an output voltage. The input is the value from the temperature sensor. And let's say this is, I'm going to write, proportional to temperature, to TEMP, in degrees Fahrenheit or whatever. That as temperature goes up, Vin goes up, and as temperature goes down, Vin goes down. Okay, and we want to control the heater. Well, let's draw a characteristic that we want, and then figure out how to do that with a circuit. So if I'm going to draw a plot here. And on the horizontal axis, I'm going to put Vin, right? That's the input from the temperature sensor into the comparator. And on the vertical axis, V out. That's the output of the comparator. And let's figure out what we want. Let's say that there's some temperature that we want to hold. Remember, Vin is proportional to temperature. And let's suppose that temperature is right about there. There's some voltage, some threshold, some reference against which we're comparing. So I'm going to call that Vref, V-R-E-F. And that corresponds to the voltage that corresponds to the temperature that you want to hold, let's say, in your house. Okay, so let's start with the temperature low. If the temperature is low out of the temperature sensor, at the temperature sensor, then the voltage out of the temperature sensor into the comparator is somewhere down here, right? That's low temperature. So, and then let's suppose, so you're somewhere down here. You would want the heater on, so you want V out to be high out of the comparator. And in fact, let's suppose the heater has turned on. You want the output to be high until you reach the reference voltage or the reference temperature. So your house is heating up, the house gets warm enough, the heater turns off. Maybe it's one of these Colorado summer days where it's cold in the morning and warm in the afternoon, and your house heats up without the heater, right? The heater's off, but the temperature's still going up. So this is the characteristic you would want for this type of thermostat. When the temperature is low, or when the input voltage is low, the heater's on. When the temperature's high, the heater's off. Okay, so this is the kind of circuit we'd like to build with a comparator. Okay, so let's do that. So I'm going to draw the schematic, and then we'll give it a name. So there's my op amp. And I'm going to connect this op amp to VCC and VEE values. Let's say VCC is 5 volts, VEE is 0 volts or ground. And what I'm going to do, and I've put the inverting input on the top, non-inverting input on the bottom. It doesn't matter, it just happens to be the way I drew this. I'm going to put the input voltage at the inverting input, and then I'm going to put the reference voltage at the non-inverting input. Now, why did I do that? Well, if you look, because down here, when the temperature is cold, you want the heater on. So when Vin is less than Vref, you want the heater on. You want the output of the op amp to be high. So when Vin is less than Vref, that would make V2 less than V1 or V1 greater than V2, right? If you look over here, that's when the op amp had a high output. So that's how I decided, well, which input is Vin and which input is Vref? Well, figure out when one is higher than the other and you want the output on, how does that compare here? So let's continue. Let's suppose you wanted to create a reference voltage. I can create a reference voltage. Let's say I only have a 5 volt supply, right? I only have a 5 volt supply. So I'm going to take this 5 volt supply, I'm going to connect it over here, and we're going to call this whole connection, that whole power supply voltage, VCC. And so VCC, that 5 volts, is also applied across those resistors. Now those resistors, they don't look in series from the schematic, but they are in series because remember, op amps have high impedance inputs. So there is very low current going into the inputs of the op amp. It could be on the order of nanoamps where you have maybe milliamps flowing through the resistors. So let's name these resistors R1 and R2. And these resistors, again, are in series because this current is approximately 0 amps. So these resistors have the same current going through them. So you could figure out, well, then what is the reference voltage? Let's suppose I want to figure out what resistors do I need in order to create a reference voltage of 2 volts, because 2 volts corresponds to 72 degrees out of the temperature sensor. Well, you could figure that out using, well, voltage division, right? Going back to the early topics in class. If you wanted to figure out Vref based on resistor values, or likewise, you have a Vref and you want to calculate resistor values, you'd use voltage division. So this would be VCC times R1 over R1 plus R2, right? Because you're trying to find the voltage. Ooh, I did that wrong. This is R2. So you want to find the voltage across R2, which is Vref, right? That's what that node voltage is. So that's the voltage divider formula for that. And this is V out here. Let me draw this over here. Okay. Let me summarize what's happening at this op amp. Kind of give you a takeaway here, that for the output of an op amp, this circuit, and well, it's the same as the circuit over here without the resistors. So V out equals, it depends on V1 versus V2. So V out equals VCC for V1 greater than V2, and VEE for V1 less than V2. Okay, so that is like the big takeaway for all these comparator circuits. Okay. You're comparing V1 and V2, and the output is going to be based on one relative to the other. Let me throw a practical aspect in here. And so this is if you ever, in a future class or a future project, design a comparator, use a comparator. Let me move, I'm going to move something over here. I want to put the 5 volts on this side so I have some room. This works as shown for a typical op amp. Okay, this works. You could take an op amp and you can do this. The problem is for cheap op amps, as you saw, that the output sometimes doesn't go all the way down to VEE, and the output doesn't sometimes go all the way up to VCC. And maybe you want that. Maybe you want those values really close, in this case, to 0 volts and 5 volts. Not like, oh, I lost my screen. Not like 1 volt and 3 volts, right? So you want to get those values closer. And so there's another kind of op amp integrated circuit that is specialized. It's exactly for comparators. And let me draw kind of a big op amp here. So I'm going to erase this, but because I need this room. But let me draw it even bigger. So one big op amp. Imagine this. So this is how that specialized comparator integrated circuit works. Imagine you have your VCC and your VEE, and let's connect VEE to ground. Right, so down here it's connected to ground. And here's the output, V out. Inside, I'll show you the behavior first, and we'll replace this with a transistor, but I'm going to draw a switch. Inside these specialized circuits, you have what's essentially a switch. It's really a transistor, but let's draw it as a switch for now. So when V1 is greater than V2, this switch opens up. When V1 is less than V2, this switch closes. Okay, so what that does is that when you want the output to be low, the switch connects the output to ground. So you get 0 volts. The problem is, as shown, when this circuit wants V out to be high, it opens up the switch, and V out is just floating. It's not connected to anything. So what you do as a circuit designer, as a project designer, you actually put this resistor here. You put a resistor, and that resistor, it's called a pull-up resistor. So I'm gonna put R, and under it, I'm gonna write pull-up, P-U-L-L-U-P. And what that resistor does is it connects the output to, let's say this is 5 volts. It connects the output to 5 volts, and this might be a 1K ohm resistor. So that's a typical value. And so when this switch is open, the output, as long as there's not much current coming out of the output will be high, right? So V out, this node is connected to the 5 volt source. When this switch is closed, the output is connected directly to ground. So it goes all the way down to ground. And then, well, you have 5 volts here across a 1K ohm resistor, you get 5 milliamps flowing, and that's okay, but the output is still ground. So a pull-up resistor is a resistor that you connect to the output of this chip or any chip, any integrated circuit, that pulls the voltage up to close to the power supply value unless the chip pulls it down. Okay, so this output will be high until the switch closes. So that's how this circuit actually works. So what you need a resistor here if you're using a specialized comparator chip, and that would be, again, typically it's in the 1 to 10K ohm. Let's just write 1K ohm resistor here. So that right there is the schematic for what we call an inverting comparator. Okay, it's an inverting comparator because if you look at the characteristic that we drew, what we wanted, when the input is high, the output is low. When the input is low, the output is high. They're the opposite in sense. So that's why this is an inverting comparator, and it works well as a thermostat. Okay, just one more thing to show you on this pull-up resistor. This is not really a switch. I'm going to draw in what it is. I'm going to take that switch out, and you could guess it's a transistor, right? So if I put a transistor here, and I connect a transistor like that, dot, dot, dot over here, this chip is actually either saturating that transistor, which means 0.2 volts or less between ground and the output, that's a low output, or this transistor is in cutoff. And if the transistor is in cutoff, that's like an open switch and the output goes high. You will see this referred to as an open collector output. Okay, so if you hear open collector output, that means you have a transistor essentially that's not connected to anything inside this chip. If I don't connect anything on the outside to this, then the collector goes to nothing. It's an open collector output. This is, again, common on chips, on digital chips especially, where you have to provide a pull-up resistor. Okay, so that's a what I would call a simple comparator. There's one threshold, and you're making a comparison against a threshold that doesn't change. And so this circuit implements this characteristic that is appropriate for a thermostat. Okay. All right, again, if you have any questions on this, go ahead and shoot me a chat or go ahead and shout them out. This comparator is very useful. It works, and most of the time. There are some applications where a simple comparator is not appropriate, and let me let me show you that. Let me, what I'm going to do is I'm going to erase kind of the top here. See if I can do this without messing up my whole drawing. So let's take a look at what happens. In fact, I can even get rid of this heater. Let's take a look at what happens if you have a little noise on the input. And it may not matter for a heater, but it may matter for other applications. Let's do a drawing of, so we have V in. So that's V in, and let's draw V in versus time. And let's also draw V out versus time. And let's also draw a threshold in. So let's suppose you have a threshold, or I've been calling it a reference voltage, that falls somewhere right there. So that's V ref, as we've been calling it on the drawing. And so that's this V ref down here. Let's take this voltage input and let's assume it's kind of an increasing voltage that has some noise on it, right? It's just, I'm just going to draw some noise on it. It's going up like that. I'm exaggerating it, but. So what this would do is on the output, what you would see is, well, when V in is less than V ref, the output is high. So I have a high output. And then as soon as the input crosses the reference, the output goes low. Well, with this noise, let's see, I've crossed the reference and then I've also gone below the reference. Let's see here, and then I've gone above the reference, right? And then I've gone below the reference again. Let's see, 1, 2. So 1, 2, 3, 4 here. 1, 2, 3, 4. I think I have them kind of lined up. So you would get this kind of characteristic. If this were a heater and with just a little bit of noise, if the heater could react fast enough, it probably can't. You would have the output high and then low, high as the temperature hovers right around the reference. That may be okay for a heater circuit or maybe a motor control, but it probably wouldn't be okay. Let's say if you were building a comparator that compares light intensity from a sensor, from a laser that's meant to count people. In other words, you might have a laser, right, and then a light detector and a comparator. And so when someone breaks the beam, the count goes up, right? And so for each time someone breaks the beam, maybe each falling edge, the count goes up. Well, if you have many transitions, you count the edges. You would actually count what, like 3 people crossing through this beam if you had a little noise on your sensor voltage. So what you'd really like to do is you'd like to have a different kind of circuit that has maybe 2 thresholds. The takeaway from this before we move on is that a simple comparator like I've drawn here with a single threshold, it's good, it's fine, it works, but it's not good in noisy environments if that matters to you. Okay, so let's go and let's create another circuit, actually another characteristic, and then we'll create a circuit for that. So the solution to this is what's called an inverting comparator with hysteresis. It could be non-inverting. It's just we're using a thermostat that needs an inverting comparator. But I guess the point here is that it has hysteresis. So what we would like is this. We would like to have a circuit let's draw the output versus input characteristic. It says Vn. So we might want something like this. And this is how your thermostat in your house, your apartment, your condo really works. If you notice, your heater doesn't turn on and off every time the temperature varies by 1/100th of a degree, right? Your heater typically, let's say your house is cold, you turn the heater on. It typically warms the house up to, make up a number, 70 degrees Fahrenheit. And then the house might cool down a little bit, maybe a degree, 69 degrees Fahrenheit. And then the heater turns on. But it's not like the heater's turning on and off every 2 seconds as the temperature varies, 1/100th of a degree. So that requires 2 thresholds. So here's what the heater's doing in your house. Again, imagine the temperature sensor has an output, and that's the input to the comparator. So when the temperature's low, the input voltage is low and the heater's on, right? And so at some point, the house gets warm enough, the heater turns off. So I'm going to actually say that's the transition in that direction. Heating up the house, heater turns off. Okay? And then what's allowed to happen is the house is allowed to cool a little bit. So I'm coming down this way, right? I'm going down this direction here. I went up here, down here. And then at some temperature, a little bit lower than where the heater turned off, the heater can turn on again. Right? So this is implying 2 thresholds. And I'm going to call that threshold VA, and VA1 is this upper threshold, and VA2 is this lower threshold. And in fact, so the house was cold, the house heated up, got warm enough, heater turned off. It's one of those Colorado days. You could actually have the house heat up from external sources, the sun. So the temperature can move like that. But the point of this plot is that, let me not draw, that's confusing. The point of this plot is that the heater will only turn off at VA1, and the heater will only turn on at VA2. And there's this band in between, and that band in between is called the hysteresis band. And it's VA1 minus VA2. Okay, so this is good, because what happens, in fact, let me draw what this does on our circuit. We'll talk about the circuit that does this in a minute, but let's talk about how it solves our problem. This is time, this is V in, this is V out. And so let's suppose now we have 2 thresholds. The upper one is VA1. The lower one is VA2. And then we have our noisy signal. So now let's have the noisy signal go up and down. Let's make it really noisy. I mean, kind of make that go above. So maybe that noisy signal does something like that. And let's look what happens. So the heater is on. So let's suppose the house starts out cold. The heater is on as long as the input voltage is less than VA1, right? You don't turn the heater off until VA1. So I have an output voltage here, V out, that is high until the first crossing of VA1. And I'm going to exaggerate this noise. I really want to exaggerate that noise here. Something like that. Okay, so at that point, we hit VA1, the heater turns off. And even though this signal this voltage hovers around VA1. Remember, as soon as the heater turns off, we're not paying attention to VA1 anymore, we're paying attention to VA2. We're going to build a circuit that does this. So this noise crossing that threshold doesn't cause a change of state of the heater. This does right here, the first time we cross VA2, right, coming on the downslope there. So you don't get this characteristic, you don't get this response where you're crossing a threshold multiple times because of noise and you get turning on and off. Here, you get a nice clean response. So that's what a comparator with hysteresis does for you. This happens to be an inverting comparator because when the input voltage is low, the output voltage is high. Okay. So, and again, if you have any questions on this, go ahead and shout them out or shoot a text. Let's build a circuit that does this. Okay. So let's draw that over on the left. Oop, I lost my video. That's why I got bright in here. Okay, so we're going to create a circuit that does this. Okay, let's start out with the op amp in the center here. And let's call this V in at the inverting input. And so what I'm going to draw is essentially the same as the simple comparator. We have VEE, VCC. Let's say that's 5 volts. And let's create our voltage divider over here. I'm going to extend that down a little bit. All right, so that's exactly what we had before. Let me add the pull-up resistor. You know why that's needed now, so that you can get a high at the output. I'm going to call that R4. I'll show you why in a second. So there is the, well, that's just a simple comparator. And I'm going to add just one component to cause this to happen. I want the output to affect the threshold. In other words, when the output is high, I want the threshold to be VA1. When the output is low, I want the threshold to be VA2. Okay, where this is VA right here, right? VA is that node connected to the non-inverting input. I'm going to do that, what I just talked about, with a single resistor connected to the output called R3. Okay, so that lets the output influence the threshold. And I'll show you how in a minute. This is not negative feedback, right? This is not negative feedback because I'm going from the output to the non-inverting input with that resistor. And that is, that's the opposite. That's actually positive feedback, so it's not negative feedback. And again, you can't count R4 as negative feedback in any way or any other connection. There's no connection between the inverting input and the output. So this is not a linear amplifier. This is some kind of comparator. It's an inverting comparator with hysteresis. Let's figure out what VA is based on Vout. We know Vout influences VA. Okay. The output is either in a high state or a low state, right? Let's just suppose at first that the output is in a low state. Let's suppose let's suppose V out equals 0 volts, right? It's the case where the temperature is high or whatever. So that's the case. Let's figure out what VA is. Well, in this case, right, let's isolate VA from the circuit. Let me redraw this a bit. I have a series R1 and R2, right, going from 5 volts to ground, VCC to ground, R1 and R2. And here's my node that corresponds to VA, right? So this is this part of the circuit right here. Now, when the output is low, 0 volts, R3 connects between the VA node and the output node, which is 0 volts. Right? So R3 connects between VA and 0 volts. On this diagram, I can draw that like this. R3 connects between VA and 0 volts. Okay? So what I could do here is I can actually calculate what VA is. Right. Now, I didn't actually move the resistor. I've just electrically changed, because V out is 0 volts. What is going on here? What is connected to the other side of R3? But VA will equal, let's use voltage division, VCC times, right, the ratio of the resistance across which you're trying to find the voltage, which is R2 in parallel with R3. Right, it's R2 in parallel with R3, over the sum of the series resistances, R2 in parallel with R3 plus R1. Okay. So notice this, compared to when if I take R3 out, I have a voltage divider. If I put R3 in, what happens is R2 and R3 become smaller in resistance compared to R2 alone, the way it was before. So R3 actually causes a smaller resistance on the bottom, equivalently, and it causes VA to go down, VA to be a lower value than it would without R3. So this is actually VA2, right? It's the lower value of the thresholds. If now I consider, well, what if V out is high? V out is 5 volts. Right, so I'm down here in temperature. So the circuit, you turn it on, V out is 5 volts. What is VA? Well, we can draw that here also. I have VCC, which is 5 volts, a resistor, another resistor, and a ground. So this is R1, R2, VA. And now let's figure out where R3 goes. R3 goes between VA, right? It connects to the VA node, and V out. But at this point, V out is 5 volts, right? So V out is high. V out is 5 volts. So I want to connect R3 between VA and 5 volts. So now electrically, I've moved R3 up to the top here instead of at the bottom, right? Just electrically, R3 is connected to 5 volts instead of 0 volts, because V out is, well, high here. And I can write this voltage division equation again. It's same form, different values. Let's get rid of this V out. Right, it's the resistance across which you want to find the voltage. We want to find VA across R2, so that's R2 over R2, right? The sum of the series resistances, R2 plus R1 in parallel with R3. Okay, and if you have R3 in parallel with R1, right, compared to just having R1 alone without R3, you've made this equivalent resistance up top smaller. And in voltage division, what that does is that tends to pull the voltage VA up higher than it would be if you left R1 alone without parallel R3. So that means that this is actually a higher voltage than VA2. This is actually VA1. Okay. And so you can do this. Let's suppose you want to design an inverting comparator with hysteresis. You would choose VA1 and VA2. You would say, I want the voltage corresponding to 72 degrees Fahrenheit here, and the voltage corresponding to 69 degrees Fahrenheit here, and the heater is going to vary between those two temperatures. Those would be your design values. You would pick R4 to be 1 k ohm, right, or whatever, a pull-up resistor, and you're designing for R1, R2, and R3. So these are the equations that relate R1, R2, and R3 to your threshold values, VA1 and V2, and some chosen VCC value. So what you could do is, well, wait a minute, you have 3 unknowns, R1, R2, and R3, and you have 2 equations. So what you would have to do is you would have to choose a value. Let's say choose R3. You would typically choose R3 to be some big value because you don't want to take a lot of current here and create a voltage divider between R4 and R3. But you'd choose R3, 100 k ohms. And then you would use these 2 equations to solve for R1 and R2 to get the thresholds that you designed for. Okay, so that's how you do that. There's an easier way. This really, I wanted to show this to explain why the thresholds change based on the output. That's what these show. If you, so there's an application note. Application notes are produced by manufacturers. They're published by manufacturers. They show you how to use their parts in practical circuits. So I think it was Texas Instruments that published an application note that has lots of op-amp circuits in it. One of those circuits is a comparator with hysteresis. And I've posted that on the webpage. So if you look in, I think it's under the lecture notes, you'll see an application note that has this circuit in it. It also shows how to use a design process that simplifies what I described in a way to find R1, R2, and R3. Okay, so this is what you would do. We'll take a break after I describe this design process. What you would do is, let's list the steps here. So you have a VA1 and a VA2 corresponding to your application. You've either made it up or you were given specifications, right? And you're given a VCC. You would use this design process to find R1, R2, and R3. Okay, so it's essentially parameterizing what I described on the left. The first step is to calculate the hysteresis band, which is the difference between VA1 and VA2. Okay. And then you're going to calculate this parameter n. It's just a value that's used as an intermediate value in this design process. And that's delta VA over VA2. Okay, so again, you've chosen VA1 and VA2, so you can calculate these values. You would then choose R3, and actually R4 also. So you would choose large R3. What's large? 100 k ohms. That's about as high as you want to go for a circuit like this that has a typical op-amp. And you'd also choose a reasonable R4. And I'm going to say 1 k ohm, because you want R3 much greater than R4, or you have a voltage divider over here, right? Potentially you will lower the output voltage when the op-amp intends the output to be high. So this is just a rule of thumb. Choose a big R3 in that range, a smaller R4. And then you calculate your values, R1 and R2. So R1 would equal N times R3. 5. R2 equals, well, this expression here, R1 in parallel with R3 over VCC over VA1 minus 1. Okay, so now you have R1, R2, and R3, and R4, and you will get the thresholds that you want. you can use either one of these processes, the one I've described, which I think is easier on the right, or on the left, you could solve for these simultaneous equations after choosing R3. Either will work. I just think the process on the right is a little easier. Okay, so a comparator with hysteresis establishes two thresholds. It gives you noise immunity. It acts more like a real thermostat in your house, giving you two thresholds. And this is how you would design it using an op amp. Okay. All right. So let's do this. Let's take a break now. My clock says 5:20, so let's round up to 5:21. Let's come back at 5:31, and we'll resume class there. So stretch your legs, grab a drink of water, and we'll resume there. I'll see you in a few minutes. Okay, let's get started again. Welcome back from the break. If someone can hear me, please shoot me a chat. Thank you. So I kind of wanted to conclude the op amp discussion. So we finished up our discussion on op amps, just saying, you know, like I started this discussion today, here's what's inside an op amp, and you should be seeing a schematic on the screen now, by the way, of an op amp. This is what's inside one of the op amps, and you could worry about everything that's going on here and what these transistors are doing, and IC equals beta IB, and what all these cascaded gains are doing. Or you can treat the op amp as a single block. Now, someone has to worry about this. They have to design the op amp. But from a circuit designer perspective and from a user, we just care that this is a high gain differential amplifier, and you apply power supply voltages, and it behaves a certain way. And we talked about how it behaves, and we can build really two main different types of circuits out of it. So where's my decision tree here? And so let me bring this up. So I'll go back to this decision tree just to remind you in concluding op amps that if you have an op amp circuit, you're going to do one of two things with it, either in analysis or design. You're looking at or designing either a linear op amp circuit like an amplifier, or one of the circuits you analyzed during your homework, a summer, a differentiator, something like that, but it has negative feedback and it acts linearly, or you're designing a comparator or analyzing a comparator. And then just to review at the bottom, what we're doing when we look at a linear op amp circuit is we're deciding, well, do we know the circuit? Is it a common circuit where you know the gain? And if not, you use the negative feedback approach. And so, you know, if you know it's an inverting amplifier, you know the gain from the last class. And then if you don't have negative feedback, you're dealing with a comparator. So that comparator is either a simple comparator with a single threshold, like I showed you at the beginning of the discussion of comparators, or it's a comparator with hysteresis, with two thresholds and a hysteresis band. Okay, so we've covered all four of these cases. And so again, I would, when you're looking at op amp circuits for homework or for a quiz or whatever, you know, grab this slide and use this decision tree. Okay. So what we're going to do now is we're actually going to step into the next topic. So we just covered op amps, and we talked about comparators, and comparators give you an output, a high or a low. Right, you can consider that a true or a false, right? Is one voltage greater than another, true or false? That's what a comparator does. That's a very good segue into digital logic and digital systems, which use, binary systems anyway, two different levels to represent information, right? Ones and zeros, highs and lows, trues and falses. Okay, so let's start our discussion on digital topics, on digital logic and digital systems. So let's bring a slide up here. What I'd like to do is just start off with some terminology. Okay, let's start off with a signal. What is a signal? A signal is a voltage or a current that represents information, right? That's what a signal is. And it could be in volts or amps. And so when I say signal, I mean a voltage or a current. I usually mean a voltage. Usually I speak in terms of voltages when I talk about signals. An analog signal takes on a value or a voltage in a continuous range. So an analog signal can be something like 2.62 volts or 1.34 volts or 0.862 volts. So it can be any value. And just like if you looked at your voice from a microphone on an oscilloscope, those voltages are over a continuous range. They're not discrete. They don't have to be quantized to certain levels. They can take on any value. That's what an analog signal is. A digital signal is restricted to a few ranges of values. Okay. It could be binary. We'll get to binary in a minute, where you have two ranges of values, two ranges of voltages. And there is such a thing as multi-level signaling, where you could have more than two ranges of values. We're not going to dig into that, but just to point out that digital signals are not necessarily the same as binary signals. Okay. Binary signals are digital signals. They are restricted to two ranges representing logic values. And you can call these logic values really whatever you want. They're just two different values in a set. So 0, 1, off, on, no, yes, false, true, red, blue. Like you can name them whatever you want. I'll typically use 0, 1, off, on. Well, I'll use all these at the bottom, depending on the context of the problem. So we're gonna talk about this now. First, what I want to do is I'm going to switch over to the whiteboard and start off with kind of a comparison on why you would use analog versus digital. Let me switch over to the whiteboard here. Give it something to focus on. Okay, so let's talk about analog and digital signals. So I'm going to draw a plot here that shows an analog signal and a digital signal. Okay. So analog might look something like this. So this is a voltage versus time. Make sure this is focused. So an analog signal can, again, it might be a voice signal, it might be a video signal, but it might do something like that over a continuous range. That's a voltage versus time. And a digital signal might look something like this. Again, it's a voltage versus time, but it might, in fact, let me use a different color here. It might take on values, voltages that look like this. Just making something up here. So the analog value, it can be anything, positive, negative. The digital value is restricted to 2 ranges. And just for simplification, I will modify this in a second. But just for simplification, let's just say that that red line, the line across the center, decides whether you interpret the voltage as a 1 or a 0, right? So 1, 0, 1, 0, 1, 1, 0, 1. So you pick some point in time where you make a decision, kind of a regularly spaced interval, where you decide is the value above a threshold or below a threshold. I'll modify that in a second. This is simplified, but good enough for this example. And so both of these signals contain information. They both encode information in a voltage. Now, in a real system, noise is present. So in any circuit, there's going to be noise. Noise comes in various forms. There's the most common is thermal noise. So as charges randomly move in conductors and resistors, usually considering the noise from resistors or any active electronic component, the random movement of charge causes voltage to fluctuate. And that fluctuation actually is pretty well behaved. It's usually considered white Gaussian noise. So additive white Gaussian noise is additive. It's added in. It's white. White is a color that consists of all frequencies. So it exists over all frequencies, and it's Gaussian because in the time domain it takes on a Gaussian distribution. So AWGN is something you'll hear, but you don't really have to know that for this class, but I want to mention it. And so noise is added, and that does something to your signal. It corrupts it. So versus time, your analog signal, let's say the noise looks like this. It's gonna have this noise added to it. Right. So this might be the input to your system, your circuit. This might be the output, and you get noise added. Now, that noise is always present. It's always present. You may or may not care about it. It may or may not bother you that you hear a hiss in your audio, or maybe you can't even hear the hiss. The noise is so small, but it's always there. In an analog system, it is actually impossible to recover the exact information that was encoded because there's always noise present. You may or may not care about the level of noise. It may not impact performance, but it's always there. In a digital system, it's interesting because I can have, right, let's do the same plot. I have a voltage to which noise is added. And so my signal, my digital signal, might look something like this. At the output, so you can see I have noise added. And again, this is maybe the input to a circuit. This is the output to a circuit. And if I establish that threshold, right, this is some threshold down the middle, then you can still tell. You can actually still tell, do I have a 1 or a 0 encoded, right? Any value above at these regularly spaced intervals, any value above the threshold, think comparator, right? Any value above the threshold is a 1 and the value below is 0. And so I can easily see that I get this train of values, 1s and 0s. Okay, well, what we were able to do in the digital case, we were actually able to extract exactly the encoded information. So it is possible in a digital system to extract the information that you encoded, right? Now, as this noise gets bigger, and it's all probabilistic, as this noise gets bigger, you might have a noise so big that it crosses the threshold and you make a bad decision. Yes, that's true, but kind of like your hard drive, after error correction, doesn't lose your files, it's possible to encode and copy file after file after file to hard drive after hard drive without losing your information. In an analog system, you will always have the noise, and it's always present. You may or may not care about it, but it's always present. So that's one reason we use digital signaling, because it can represent information exactly and be recovered. So it can have errors, but it also can be recovered error-free, whereas analog cannot. Okay, so let's dig into this digital signaling a little bit. What I'm going to draw next, I'm going to erase this, and I'm going to draw just the V-axis here. Okay, so I'm going to erase this and talk about how we relate the signals, the voltages, to values. Okay, so let's talk about just the vertical axis. This is a voltage, and that voltage represents digital information, binary information, ones or zeros. And it's common in digital logic, digital signaling, to have what's called different voltage levels for logic. Let me put a V there. Here's an example of 5-volt logic. Okay, if you see, for example, a chip, microprocessor, something has 5-volt logic, this is how you interpret, this is how the chip interprets voltages, or you interpret an output voltage. Between 0 volts and 5 volts, that would be the typical range of 5-volt logic, you define these ranges. Remember, binary values are valid within 2 ranges. Okay, so you have to go to the specific chip and specific manufacturer to data sheet to find these. But for this one particular chip that I looked at, between 0 volts and 0.4 volts, that was considered a binary level 0, a logic level 0. Okay, between 5 volts and 2.4 volts, that was considered a binary level or logic level 1. Okay, and then in between, that's transition only. In other words, you can change from a 0 to a 1 or a 1 to a 0 through that voltage, but you wouldn't read a valid binary value there. Okay, so that's what I mean when I said that binary signaling takes on amplitudes within 2 ranges of values. Here are the 2 ranges. Just to point it out practically, if you've ever used an Arduino or if you use one in the future, some microprocessors like the Arduino and others use 3-volt logic or 3.3-volt logic. And again, it depends on the chip, but sometimes it ranges from 3.3 volts down to 0 volts, like the valid ranges. And I've seen values like 2.2 volts and 0.4 volts here. And so again, you look at the data sheet and it'll explain what a high value range is, this would be a 1, and what a low value range of voltage is, that would be a 0. And then again, this is transition only. Okay, so I drew on the last, just to simplify it, on the last whiteboard sketch, I drew a single threshold. It's not really a single threshold to decide whether a binary value is 1 or 0 when you're looking at a voltage. It's actually 2 ranges. Okay, and outside of that, it's not valid. You can't tell. You have a broken chip or something's wrong with your circuit. Okay. All right. So this is how you represent a 1 and a 0. Let's talk about digital words. So a digital word consists of bits. I've been using this word bit. Bit stands for binary digit. Okay, so BIT or BIT, that's what a bit is. It's a binary digit. And if you take bits and you put them together to form values, that's called a word, right? You represent info with multiple bits, and we'll do examples of that. And there's a special word you've heard of called a byte, right? That's an 8-bit word. Okay, and then talked about less often, but often used for hexadecimal representation, which we'll get to, is called a nibble. It's a little byte, kind of. It's actually a 4-bit word. Okay. So when I say bit, I mean a 1 or a 0. When I say word, I mean multiple bits. If I'm being specific about an 8-bit word, it's a byte. And if I'm talking about a 4-bit word, like we do when we talk hexadecimal, I'll talk about a nibble. Okay. And again, so I'm going to erase this, interrupt if, go ahead and unmute or shoot me a chat if you have any questions about this. Let's talk about representing useful values with digital words. Okay, so let's do that. So what I'm going to do now is erase this. And I'm going to take you back to binary numbers. Actually, I'm going to take you back to numbers, right? What numbers mean. So we look at values all the time. We look at decimal values all the time, and we don't even think about interpreting them. We just understand that 743 is greater than 64, is less than 1028. We don't work at interpreting them. But what I'd like to do is relate decimal numbers to binary numbers and show you how this works. So if I have, let's just say I have a decimal number in decimal. And decimal is base 10. That's what decimal means. And base 10 means you have 10 symbols to represent per digit to write a number. You have 0 through 9, right? Those are 10 symbols you can use for each digit. And let's do an example. Let's take an example, 743.2. Okay. We all can interpret that. We can look at that. We have a feel for it. We understand it. Let's break that down, though, into how we're interpreting this value so that we can do the same thing with a binary number. So what we're doing is we're actually comparing not only just what the symbol value is, but we're looking at the symbol's position relative to the radix. So the decimal point in decimal is a radix generally, and it separates the integer part from the fractional part of a number. Okay, so 743.2. So what we're doing when we look at the 7 is we're actually considering that value, 7, and we're looking at its position relative to the radix, which is 3 positions over. But we're gonna index these positions just to the left of the radix, starting with 0. So that's 0, that's 1, that's 2. And so I would say that this is 7 times 10 to its position relative to the radix, which is 7 times 10 to the 2. That's how we interpret 700, right? The next digit is a 4. And again, we interpret that digit as a 4. And its position relative to the radix, and again, position 0, position 1, this is 4 times 10 to the power of 1. And likewise, right? So plus 3, the next digit, times 10 to the power of 0. I'm calling that first position to the left of the radix, position 0. And then the 2 is to the right of the radix. And so we interpret that as 2 times 10 to the power of -1. We're calling positions to the right of the radix negative positions. And that's 1 position to the right. So that's a -1. So So this is what we mean. 700 plus 40 plus 3 plus 2 to the negative 1, 1/2, right? So now let's do the same thing with a binary number. Right now that we've refreshed how we interpret decimal numbers, let's talk about binary. So binary. Oh, sure, go ahead.
Can we quickly just spell radix?
Oh yeah, radix. So this is the radix. Yeah, thank you.
Thank you.
Okay. And that's a good question. I hadn't had anybody actually ask me that. So binary is base 2, which means you have 2 symbols to deal with. You have 0 and 1. You have 2 symbols for each digit. So when we're looking at a binary number like 1, 1, 0, 1.1, and we interpret that, we're doing this. Again, we have a radix, separates the integer part from the fractional part. And we have, let's see, a 1. Let's go to the leftmost position. It is in position 0, 1, 2, 3. So it's a 1 in position 3. So it's 1, right, times the base. It's not base 10, it's base 2, to the power of the position, which is 3, 0, 1, 2, 3. Okay. You go to the next digit. So it's a 1 times the base 2 to the power of the position 0, 1, 2, and so on. Right, this is a 0 in the next digit times 2 base to the power of 0, 1, right? Plus a 1 times the base to the power of the position 0. And then plus we have, it's just to the right of the radix, we have a 1, right? Do the same thing, times the base to the power of the position, negative 1. Okay, so this is actually converting this, if you interpret now these values in decimal, we're converting from binary to decimal. This is an 8, right? Plus a 4, plus a 0, plus a 1, right? Plus a 0.5, 1/2. So this is 13.5. Okay, if I add those up. So 1101.1 in binary is 13.5 in decimal. Now it's a little confusing because both of these are valid decimal numbers. So how do we tell the difference? How do we tell we don't mean 1101.1 in decimal up here, other than I've written it here? It's convention when you're dealing with multiple number systems like this to use a subscript that is the base. Okay, so 1101.1 base 2 is equal to 13.5 base 10. So that's how we can differentiate between these two number systems. So in explaining decimal values compared to binary values, I've also shown a way to convert from binary to decimal. You just interpret the values with the digit times the base to the power of the position, and then you can convert those to decimal. If you're going the other way, right, let's talk about converting, decimal to binary. Right, let's do that. Let's suppose I have a number, 23 base 10, and I want to convert that to binary. Well, if you noticed up above that you were creating a number out of powers of 2, right? So you have 2 to the power of n, where n is an integer, and then you're going to add up those values for different n's. And so that's what you have to do. You have to figure out what values of 2 to the n, where n is, you know, negative values and positive values, integers, how do you sum those values up to get, well, the decimal value you want? An easy way to do that is to figure out, okay, how do I create 23 out of powers of 2? So you can think of powers of 2, right? 2 to the 0 is 1, 2 squared is 2, 2 to the 1 is 2. 2 squared is 4. So you have 4, 8, 16, 32, 64, 128, right? Dot, dot, dot. You can think in powers of 2. And so what you do is you take the biggest power of 2 that will fit into 23. All right, so 23 is, let's see, 16 will fit in, 32 won't. So it's actually 16 plus something, right? So I got to add other values that are powers of 2. If I denote a remainder after I've taken up 16 of the 23, right? I can then create that remainder out of powers of 2. So let's see, 23 minus 16 is 7. So that's my remainder. So I have to create 7 out of powers of 2 to the n. Okay, so let's see how can I create 7? Well, 7 I can create out of, well, not an 8, but a 4, right? So 7 plus 4. And so now if I have 16 plus 4, 23 minus that, my remainder is 3. 16 plus 4 is 20. I have 3 to account for. And then I can create 3 out of powers of 2. That'd be 2, the remainder is 1, 1, the remainder is 0. So 16 plus 4 plus 2 plus 1 is 23. All right. Each of those values is a power of 2. So I really have, right, 2 to the power of 4 plus 2 squared plus 2 to the first power plus 2 to the 0. Now, also, if you notice the positions of the digits in binary, if you don't see a radix, assume it's all the way on the right. Just like if you look at a value of 23, there's no radix, there's no decimal point, you assume it's all the way on the right. So this would be 2 to the power of 0, 2 to the power of 1, 2 squared, 2 third, 2 to the fourth, 2 to the fifth. And so now you can look at where do I need ones? I need a 1 here, I need a 1 here, I need a 1 here and here. And I don't need a 2 to the power of 3 in there. And again, you can have leading zeros. I could put a 0 there, right? That doesn't affect anything. I could even put a 0 here. It doesn't affect anything. But what I would say is that 23 base 10 equals 10111 base 2. Okay, using that process. Okay, so that's how you would convert decimal to binary. So you'll do some of that. Let's talk about another numbering system. And again, if you have any questions about this, just please unmute or shoot a chat. There's another common number system called hexadecimal. And I'll spell that out. If you've seen the movie The Martian, it's been a while since I saw it, but there was a scene where right, the guy stuck on Mars had to communicate back to Earth, and he figured out there was a certain resolution of camera angles he could use. I think it goes like this, like camera angles he could use to communicate data, communicate information back to Earth. And he figured out, hey, it's 16. He can use 16 different angles. So he was encoding values in hexadecimal, because hexadecimal is actually base 16. All right, so hexadecimal, base 16. And the way I like to describe this is actually just to start counting. Start counting in decimal, start counting in hex. So if we do a table where this is decimal and this is hex, short for hexadecimal, we can just start counting. We could say, okay, decimal 0. What is decimal 0? What is hex for decimal 0? It's 0. Decimal 1 is hex 1. Decimal 2 is hex 2. So let's look at what we're doing here. I'm counting up in decimal with a digit until I exhaust all of the possible symbols I have for that digit. And then what do? I reset that digit to 0, and 1 digit to the left I increment. So that's a 10. And then I go 11, and so on. I'm gonna draw some lines here to keep my table straight. So you do the same thing with hex, except you don't have 10 symbols, you have 16. So ... when you get up to 9 in hex, you still have the symbol 9. When you get up to 10, I'm going to draw another line here so I keep all this straight. When you get up to 10, you haven't run out of hex digits because you have 16, and the next digit is A. Okay, and then the next digit, right, as you increment, is B. And so as I count up in decimal, I have 12, and the next digit, and the next symbol is C in hex, and 13 is D. And I still haven't used up all my 16 symbols. So I have 14 E and 15 F. So 0 through F, if you count them, right? Here's 9. Here's 10 symbols plus these 6 symbols. You get 16. So now, once I've exhausted all of my symbols for that digit in hex, what do? I just like I did with decimal, I reset that digit back to 0 and increment the next one. So 16 in decimal is actually 10 in hex. And there's a reason. I'll show you why we do this. There's a reason to this madness here. And then 17 is 11 and ... right? So you could keep counting like that. Let's talk about converting binary to hexadecimal. One hex digit represents 16 values, and 4 binary digits represent 16 values. So you can actually represent 4 bits of binary values, 4 bits, with 1 hex digit. And that's convenient for software. You don't have to write as many digits. So let me show you an example of that. If I have a number, I'm going to make up a number. 1, let me spread this out. 1 1 0 1 0 1 1 1. And this is a binary value base 2. And I assume the radix is on the right if there's no radix drawn. What I can actually do is this. Since 4 bits represents 16 values and 1 hex digit represents 16 values, 16 different symbols, right? I can actually break this binary word up into, starting at the radix and going to the left and right if I have a fractional part. I can break it up into 4-bit words, a nibble, right? Each one is a nibble. And then I can convert each one of those nibbles into a digit. So in this case, I have, let's see, 2 to the 0, right? Remember how you convert 2 to the 0. This is a 1. This is a 2, the next bit. This is a 4. So this is actually a decimal 7, right? And the equivalent hex digit is a 7. So that's equal to 7 base 16 also. So I've created a digit of hex out of a binary 4-bit word. Let's move to the other 4-bit word over here, this other nibble. This is actually, let's see, 1 plus, this is a 4, and this is an 8. Right? Plus signs in there. And so 8 plus 4, that's 13. That equals 13 base 10. And 13 in hex is a D, as in delta. And then what you can do is you can actually concatenate those values together. This is equal to, this whole binary number is equal to D7 base 16. Right? So D7 base 16 is equal to 11010111 in binary. And I can just concatenate those because remember, 7, each digit is like multiplying by the base. So if I shift a digit if I shift a digit in binary, it's like multiplying by 2, right? If I shift a digit in hex, it's like multiplying by 16. If I shift 4 digits, right, 1 nibble over, it's like multiplying by 16, which is what I've done here. Okay. Just like in base 10, if you add a 0 or if you shift left or right the decimal point, you're multiplying or dividing by 10. Okay, so 2 points here. 1, here's how you convert from binary to hexadecimal. You start at the radix, you group into 4 bits, and then you convert each nibble. Oh, I lost my board. You convert each nibble into a binary or a hexadecimal digit. Okay. Let's do one more example. I want to show you some leading and trailing zeros. I was making 2 points there. Let me step back. I showed you the conversion point. The other point is that now you can represent 4 bits at a time with a value, right? So if you're if you're programming software for an Arduino and you have to represent these binary values as setting some register somewhere, instead of writing 11010111, you can write D7 and you can specify it as a hex value. So you can see as you have maybe 32 bits, 64 bits, it's more compact to show on a screen or to type in these hexadecimal digits that can represent 4 bits at a time. Let's take another value. Let's say you have 1. Let's do 1 1 0 1 0 1 1 0 0 point 0 1 1. Let's suppose that, and there's a radix here. Let's suppose that's your number that you would like to convert to hexadecimal. You follow the same process. You start at the radix. You divide the binary number you split it up into 4-bit words. If you get to a point where you've run out of digits to create a 4-bit word, that's okay. You can always add leading zeros. Like it's like taking the value 126 and adding a 0 in front of it. I mean, it doesn't change the number in decimal. So I can add these leading zeros. I can also add trailing zeros. So I only have 3 digits here. I can always add a trailing 0. It's like having a value 126 and writing 0.0. It doesn't change anything, right? So now I have, again, I can do the same process. I convert this value, which is a like this is 1, 2, 4, 8. This is a 12 base 10, and a 12 base 10 is a C base 16. So right, you don't have to remember this table out to infinity on the left. You just really have to remember 10 through 16. I'm sorry, 10 through 15 is A through F. Okay, and so let's see. This value here, this 4-bit word is 1, 2 plus 4 plus 8. This is a 10 base 10. Right, 10 base 10 is an A alpha base 16. This is a 1 base 10, which is a 1 base 16. Okay. Over here to the right of the radix, we have a, let's see, 0, 1, 1, 0. So it's 1. So you still interpret this nibble over here, like it's separated from the rest of the number. In other words, I look at this value, the 0, and this is in the 2 to the 0 place. I look at this 1, and it's in the 2 to the 1 place. This is in the 2 squared place, and 2 cubed, 2 to the 3rd place. So I'm still interpreting this no matter where that nibble is in the whole binary number. I'm still interpreting it the same as every other 4-bit word here. So this would be 2 plus 4, and that would be a 6 base 10, which is a 6 base 16. So now I put all these numbers together, and I would call this number 1AC.6 base 16. So this binary value converted to hexadecimal is 1AC.6. Okay. All right. So this is how you represent numbers with binary. This is how computers do calculations. This is how computers store values in memory. This is how computers send values over the internet. It's using ones and zeros. We typically use ones and zeros because it's easy to represent ones and zeros in memory with capacitors, for example. You either have a charged capacitor or not a charged capacitor, right? And you can represent a 1 or a 0. You can make decisions, and I'll show you how, with a transistor. Either the transistor is saturated or not, and that's a 1 or 0 true or false condition. Lost my screen. And so that's a reason. One reason we use binary is because it's easy to send information with a high voltage or a low voltage. It's easy to store information. It's easy to make decisions. So what we're going to do next time is we're going to start looking at circuits that make more complex decisions than op amps. They're not just like which voltage is higher than the other voltage. It's more of a, okay, I have a decision to make with a bunch of binary inputs. I may have 2 or more binary. I might have 8 binary inputs, and there's a certain output I want out of each one of those cases, out of each possibility of cases for the input. And so how do I make a circuit that makes a decision based on that? We'll talk about some practical examples. That's going to be called combinatorial logic, okay? And we'll get to that next time. Okay, so that is all the material I would like to cover for today. In closing, take a look at the upcoming assignments. So homework 6 and 7 are due this week, and quiz 5. Also take a look at lab 4, and those associated videos will be posted shortly. I will stick around for office hours. So in about 2 minutes, I'll go on mute, and in about 2 minutes, I'll come off of mute, and we'll start office hours to give folks a chance to depart if they choose to do so. You're welcome to ask questions about any of this material or other material, or just listen into other people's questions during office hours. If you're not joining office hours, then thanks for joining the live class, and I'll see you next time. Okay, I'll go on mute now. I'll be back in a couple minutes.